Welcome everyone. I'm Norman Wildberger, and today we're going to look at what's almost surely the greatest single development in the history of science and mathematics, which is the introduction of the Hindu-Arabic number system to do arithmetic. And of course, this is not just the foundation and underpinning for modern science and commerce and most of quantitative transactions in the modern world. It's also the main subject in mathematics for young people in the years K to 6. So it's absolutely crucial that we get off to a good start in understanding the Hindu-Arabic number system. And I have quite different ideas from perhaps many educators on this subject. I don't think, in fact, that it's so valuable for young children, like preschool children, to be forced to learn the meanings of these symbols. For them to understand that this is 1 and this is 2 and this is 3 and this is 4 and so on, I don't think that's really that important. What's more important is that they learn how to count, that they learn that numbers are something that one uses to count. And in fact, it's better for them not to learn that with the Hindu-Arabic number system, but rather to learn it with this kindergarten approach that I've told you about, where the numbers are represented by rows of unit cells, and where the arithmetic is particularly simple. At least addition is very simple, just put rectangles together, and multiplication is reasonably simple. Make a rectangle whose dimensions are the two numbers we're started with. In this case, that one is there, and that dimension is there. And then count the number of cells in that rectangle. So these are very geometrical, almost physical things that young people can start out learning, long before they're able to draw anything coherent on a page. So for example, there's a pleasant game called Blokus that involves little plastic pieces like this. So I hope you can see that's a little rectangle with 4 little blue squares together. This could be a good model for the number 4, which is appearing right here. And a young person can say, let's say we're trying to count how many letters the word here has. The person could count that by saying, well, there's the H for that first one, E for that one, R for that one, E for that one. So the squares here exactly match up with the letters there. So we're counting the number of letters there, and we're obtaining, as a result, this number. This is a number. That's a better way of thinking about what a number is, actually, than a symbol like this. Might appear a bit of a controversial statement, but I'd like you to think about this thing here as being a symbol that represents this number, or this number. So in my view, to understand this Arabic system, one should really proceed in 2 steps, from the primitive system to a intermediate system, which I like to use the simplified Roman numeral system. And then a second step from there to the Hindu-Arabic system makes things, in my view, a lot clearer. So that's the approach that we're going to take in today's video. We're going to talk about going from here to here, introduce this simplified Roman system, and then we're going to talk about how to go from the simplified Roman system to the Hindu-Arabic system. And one piece of technology that's going to play an interesting role is the abacus. The abacus helps us going from here to here. Okay, so a very important video today. We're going to introduce the Hindu-Arabic number system. So a very good place to start is with the first 10 numbers. They play a particularly important role in this number system. So here are the first 10 numbers written in our naive kindergarten approach with rectangles divided up into a certain number of cells. So there's the number we were used to. So here are the various numbers, and here now we're going to introduce names for the numbers. Up till now we've only had the name for this one. We called it 1. and all the other names were created from just repeating ones. So we used to call this 1, 1, 1, 1. Now we're going to call this number 4. Now I remind you that young people can talk long before they can write. Right? So they can learn that this thing here is the number 4. They can learn that word long before they learn how to read 4, or long before they actually learn our symbol for 4. So that's the important thing. To understand first, this is the number 1, that's 2, that's 3, that's 4, that's 5, that's 6, that's 7, that's 8, that's 9, and that's 10. Now every ancient culture that had a numerical system would essentially have done something like that. I think it's reasonably fair to say. Would have introduced names for the various numbers, at least the first few. They may not all have introduced symbols for them. So later we're going to introduce the Hindu-Arabic symbols, which are yet something different from the names. But before we do that, we're going to talk about the Roman symbols, or the simplified Roman symbols, because this is a simplified Roman system here. So the simplified Roman symbols for these numbers are just what you would expect. They're just strokes of ones, one being a single vertical stroke in this case. So the way we would write this number down on a piece of paper is just to make a single vertical stroke. And now here's the number 2, 3, 4, 5, 6, 7, 8, 9, and 10 gets a special new symbol. Note that we're making a little bit of a departure from the last video. In the last video we said that it would be convenient to replace 5 with a V. We're not going to do that this time. We're going to base things on base 10 rather than on base 5. That's an aspect of why this is called a simplified Roman system. So all the numbers have strings of ones associated with them up till 10, and 10 gets replaced with this new symbol X. Now on the pictorial side, we could also do something similar. Why don't we introduce a new kind of object that represents this big rectangle with 10 cells in it? And we'll do that with color. So we'll make a little square that's colored red, and we'll agree that that one there is worth 10 of the white ones. Okay, so that's our symbolic or pictorial representation of 10. So for example, in Blockus, there would be a bunch of 10s. There's one there, another one, another one, another one, another one. So there'd be 5 10s in that rectangle there. Okay, so that's a very important start. We've got the numbers themselves, we've got the names of the numbers, we've got the symbols for the numbers if we're actually writing something down on a piece of paper. And at this level here, the crucial new thing, well, it's the idea that all the ancient civilizations had, is to introduce a larger unit to make it more efficient to write down larger numbers. So that's our first new symbol, X, representing 10. So how would this work in practice? Well, suppose we had a largish number, say that one right there, and we wanted to write it in a more efficient, more compact way. Then what we'd do is we'd look for a string of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm using the fact that I've got names now for those numbers so I can count myself down to 10. That's a string of 10. I can replace that whole string there with a single red one. A single red one is worth the same as these 10 white ones or blue ones. And while there's some more room over here, there's another 10 right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that string there can be replaced by that second red one there. And there's 4 left over. We'll just copy them there. So this original number is now represented in this rather simpler form, a multicolored form, in a pleasant way. Now in terms of our Roman symbols, the original number could be represented by all these ones, exactly 24 of them in fact. And we could have done the same thing on the level of these symbols. We could have counted off 10 and replaced it with an X, counted off another 10, replaced it with an X, and then there would have been 4 left over. So this is the basic idea that underpins all the number systems in the ancient world, and we want to keep doing it. We want to keep introducing a few more bigger symbols to deal with ever bigger numbers. So the next one in our system is the symbol for 100, or C, and that's going to be 10 tens. So this is 1 10, and here are 10 of them. And we're going to agree that this string of 10 tens can be replaced with one green square. We're going to call that green square 100, and its Roman symbol will be C. So that's the same as the symbol that the actual Romans used for 100, C for century. And then one step further, 10 hundreds, all in a row, can be replaced with one black square, which we'll call 1000, and its symbol is M, like for millennium. So for example, 1967, or the number 1967 in our Hindu-Arabic notation, would be written as 1000, taking care of that. And then we need 900, so 100 is C, so C, 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 that's 9 of them. And then we need 60, that's 6 tens. There's 6 tens right there, those are the X's. And 7 ones left over, there they are there. And a very nice way of thinking about what's going on here is that we are introducing higher denominations just as we do with money. So instead of having lots of $1 bills or $1 coins, we introduce a $10 bill. Maybe it's red, corresponding to this. And then we also introduce a $100 bill, that's green, and a $1,000 bill, that's black. And what we're saying here, for example, is that 10 of these equals that, 10 of these equals that, 10 of these equals one of those. And we could conceivably introduce some higher denominations, but for now we'll just pause at the M. The Romans, in fact, didn't introduce anything bigger than M. This is truly a decimal system. Decimal being a word coming from the Greek for 10, because our various units, starting with 1, and then 10, and then 100, and then 1,000, they're all 10 times the previous one. So 10 times 1 is X, 10 times X is C, 10 times C is M, and so on. That's what we mean by a decimal system. And we can think about this, just to iterate it again, that this is a basis for exchange. That what we're saying is that 10 X's can be exchanged for a single C. It's like a bank. If you have one C, it's like $100 bill, you can trade it in for 10 $10 bills. So arithmetically, 10 X's, in other words, that many X's equals that many C's. And that many C's equals that many M's. So this has an obvious but kind of important consequence. The consequence is that whenever we have 10 or more of any of these units, we can exchange some of them for higher units. Whenever we have 10 or more, we can go to the bank and get a bigger unit in exchange for 10 of the ones that we've got, making our number more compact. So for example, here is a number in our simplified Roman system. It's got one M, it's got a whole bunch of C's, a whole bunch of X's, a whole bunch of 1's. And this is not the most efficient way of writing this because there's, for example, 10 C's here somewhere. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those 10 C's there can be replaced with a single M. We might as well do that. And it makes everything shorter. We still have 2 C's left over. Where did this third C come from? Well, it came from 10 of these x's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those 10 x's there can be traded in for 1c, leaving still 3 more x's. But that last x there, well, that's the result of trading in 10 of these 1s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's all of them except for 1. So there'll still be a 1, 1 left. So in this way, if anybody writes down one of these Roman numbers, we can simplify it by looking to see whether there's a 10 or more of a unit, and if there is, exchanging those 10 for a higher unit. So I think you understand pretty well now how to represent a number in this simplified Roman system, using 1s, x's, c's, and m's. So that's good, but doing arithmetic with them is even better. So a natural question is, how are we going to add or multiply using these simplified Roman numbers? So here's the first exercise for today, is to have a look at a few examples of arithmetic with these Roman numbers and see if you can figure out what the answer is. So this first one, for example, we had this Roman number, which we would read as 10, 1, 1. And then plus 10, 10, 1, 1, 1, 1, 1. Or we could say 10, 10, 5, because we know 1, 1, 1, 1, 1 is actually 5. So what happens when we add these things? Well, I remind you, you're not allowed to convert to the modern Hindu-Arabic notation and then use whatever arithmetic skills you've already learned. The idea is to recognize that these numbers represent ultimately long rectangles. And we want to convert things into the rectangles and then sort of imagine what's happening at the level of rectangles and then convert back to something that's Roman. So I want you to go back to the more primitive system to understand what's happening, not to the more advanced system of the Hindu-Arabic numbers, which we haven't gotten to yet. Okay, it's of course a little bit more complicated when the numbers get bigger. Here's some numbers with some hundreds in it. Here's a multiplication, 3 times 10, 2. Here's 10, 1 times 10, 3. And here's some product involving some hundreds. This is going to be very challenging for you. This ought to be very challenging for you, all right? It ought to be. If this is easy, then, well, either you're very gifted or maybe you're cheating a little bit. So the reality is that in ancient times, arithmetic was hard. Questions like this would have stumped most people. They wouldn't have known how to do these questions just by hand. Only experts could do it with a pen and paper. First of all, pen and paper, well, paper would probably have been relatively expensive, and people probably wouldn't have been happy to waste paper making long arithmetical calculations. So what they actually did instead was to use calculators, well, an abacus. So this, of course, probably arose most often in merchants making commercial transactions where you need to make calculations. And the abacus, or accounting frame, was a very important technology that was almost universal across many, many cultures. So here's an example of a Chinese abacus, sort of a simplified one, not as many columns as usual. So there's sort of a bar somewhere, and then there's sort of 5 beads on each rod below the bar and 2 beads above it. There's also a Japanese abacus called a soroban, which is a lot like this, except that there's only 1 above the line, 5 below the line and 1 above the line. I told you I'm not very big on technology, but in fact this is quite a good technology to help us learn to do arithmetic. Let's have a look at an even simpler kind of abacus that preschool kids often play around with. So an abacus is a device, a physical device to represent numbers and to allow you to do arithmetical operations like addition, subtraction, multiplication, perhaps even division. And most cultures had some kind of mechanical devices that were in this direction. So exercise 4.2, why don't you go and get yourself an abacus if you don't already have one? Okay? They're a very good tool for learning arithmetic and becoming familiar with the way arithmetic works. I'd be very happy if young people in years K to 6 were able to trade in their calculators for abacuses. That'd be a great way of improving immediately mathematics education across the world. This, I think, is appreciated in Asian countries, but in Western countries it's still not very well accepted. But an abacus is far superior to a calculator when you're trying to learn arithmetic and mathematics, believe me. Okay, so here's a very simple kind of abacus that very young children can use. We have a frame with some rods, and on these rods are little colored beads that can slide. And there's typically 10 of them. So we've got 10 blue ones, 10 red ones, 10 green ones, 10 black ones. And I've used these colors because they represent the colors that we've been talking about, representing ones, tens, hundreds, and thousands. So what we're going to do here is we're going to think about each one of these beads as representing 1. And each one of these red beads as representing a 10. So a red bead is just like a little red square. And a green bead is representing 100. That's just like a little green square. And the black bead is representing 1,000, like a little black square. And if we wanted to, we could have more rows and we could think about bigger numbers, bigger units as well. But we'll stick to these 4 colors for now. So how do we represent a number in this system? Well, we slide over a certain number of beads. So here we've slid over 1, 2, 3, 4, 5, 6 of the blue ones. The blue ones represent 1, so we've really slid over 6. So this by itself represents the number 6. And we've also slid over 2 of the red ones. So each one of those is a 10. We've slid over 5 of the green ones. There they are there. Each one of those is 100. And we've slid over 1 of the black ones. There it is there. So what's appearing here on the right-hand side represents a certain number. And we can write down the Roman symbol for it very easily by starting from the bottom here with this 1,000, writing an M. Then for each of these green ones, we'll write a C because they all represent 100. So we get C, 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 C. And then we have a couple of X's representing the tens. And then we have a couple of ones representing these unit ones up here in blue. So going forward a few hundred or maybe 1,000 years, here is the Hindu-Arabic numeral for this. We would call this 1,526. So how are we going from this or this to something like this? Well, it's time to introduce our Hindu-Arabic number system, which has a number of key features. The first is that it's a decimal system. It's based on powers of 10. The second is that there are special symbols now for the numbers 1 to 9. We introduce more compact symbols, so separate symbols for each of the digits. We don't just write 1 and then 1, 1 and then 1, 1, 1 for 1, 2, 3. We now introduce these symbols 1, 2, 3, 4, 5, 6, 7, 8, 9 for the respective numbers whose names are 1, 2, 3, and so on. Of course, these are very familiar things, but they've evolved over time quite a lot. Although the Hindu-Arabic number system was developed somewhere around 500 to 800 AD, we don't actually know who exactly was responsible. It's probably a number of people making contributions over a long period of time. These symbols, or these digits, actually evolved over the years, were modified by the Arabs later on, and they probably achieved this kind of form only in the relatively recent past, maybe the last 500 years or so. And in fact, there's still modifications going on to these digits even today. So many of you younger people perhaps will not write a 7 the way I do. So I was taught to write a 7 with a little bar across it to not get it confused with a 1. Because back in my time, one often wrote a 1 with a sort of a base on it and then a little flag flying there. And then it became a little bit easy to confuse the 1 and the 7. Another point is that the 4 that I've written here is somehow different from other 4s. Sometimes this one here is sort of diagonally, so that a 4 looks more like this. You'll all recognize that too. And I just note even with my daughter, the way she learns to write these numbers in school is different from the way we were taught to write them. So there's still an evolution going on. Maybe in 100 years from now, they'll look a little bit different yet again. But anyway, this was one of the very important developments, the contributions that made the system work, that we have separate symbols for the numbers from 1 to 9. And then the third key feature, which is probably the most important one, even though it looks like the most inconsequential, is that we have a special symbol for nothing. We call nothing 0, that's the number 0, and we actually represent it with, in this case, a sort of a circle or elongated circle. It's important that nothing has a symbol associated to it. We saw that actually even when we were counting in one of our first videos here. We were counting tilings, you may remember, of rectangles. And at some point we counted how many ways there are of tiling a 5 by 3 rectangle with dominoes. And 5 by 3 was 15, was odd, and so there were no ways of tiling this. So the answer to our counting problem was 0, nothing. There are no ways. So this is a possible answer to a counting problem. It could easily be that you're trying to count something, you get 0. That's a very possible answer. With the Hindu-Arabic system, we now have something that we can write down on the page representing nothing, not just blank. This is very important because it feeds into this fourth key point, that the system is going to be a positional system. We're going to write down a bunch of these symbols from 1 to 9. They're each going to be in a position which records a certain power of 10. So we're not going to use these Roman numerals anymore, but nevertheless the idea of the Roman numerals is going to be in the back of our minds when we move to this Hindu-Arabic system. So let's see, how does this actually work in practice? How do we actually write down the Hindu-Arabic form for a number? Well, let's start with a number on an abacus. This number right here. So we've slid over a certain number of blues, certain number of reds, certain number of greens, certain number of blacks, and the number that we've slid over here on the right-hand side represents our number. We can count that we have 3 ones, we have 9 tens, we have 3 hundreds, and we have 4 thousands. So in Roman form, or in simplified Roman form, we would write this number down in the following way. We would write it by first starting with the thousands and writing an M for each of these thousands. So M, 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 M. And then the hundreds, C, C, C. And then we need to write 9 tens, or X's, X, 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 and then finally 3 ones. So here I've written down what's going on line by line. So this line here represents 3 ones, because we've agreed that everything on this bar is a 1. Here we have 9 tens, because everything on this bar is a 10. Here we have 3 hundreds, because everything on this bar is 100. And here we have 4 thousands, because everything on this bar is 1,000. And now, what we're going to do is we're going to write down these numbers. And we're going to write them down from right to left. Or if you like, we can read them up like this and then write from left to right. So 4 there, 3 there, 9 there, 3 there. And what is it telling us? It's telling us that there's 4 thousands. So this 4 is in the thousandth place, just like this 4 here was in the thousandth row. So we have 4 thousands. We have 3 hundreds. That's in the hundreds place. We have 9 tens. And we have 3 ones. That's what we mean by it's a positional system. So the position of each digit determines which power of 10 we're talking about. This is the ones position, this is the tens position, the hundreds position, the thousands position. And if we kept on going and we had more bars, well, we could add further numbers to the left, representing larger and larger units. So here is this point that I'm trying to make, that it's a lot easier, I think, to learn Hindu-Arabic numerals as a modification of the simplified Roman system. You can see that if you were working with numbers like this a lot, at some point you might have the idea, you might say, look, this is a waste of time having to write down all these things. Why don't we just record how many ones we write, how many X's we write, how many C's we write, and how many M's we write. Because we can use our symbols for 1 to 9 to record each of those numbers. So in other words, the symbols from 1 to 9 are not just being used to count ones. They are also being used a little bit more flexibly here to count how many tens there are, or how many hundreds there are, or how many thousands there are, and that's what ends up in the various places. So my guess is that students and learners benefit by first working a little bit with this simplified Roman system, and then realize that the Hindu-Arabic system is a step up from this one. It's an improvement on this. Somebody had a good idea. Going from here to here is a good idea. It's a very, very good idea. You might say, oh, I would have thought about that too. And maybe we should have that idea. After all, we said mathematics is common sense. But this is a great piece of common sense here, that no previous culture was able to make this jump. All right? It's a very big jump going from this level to this level. Basically from the ancient world to the modern world. It's that big a jump. Now I still have to explain the importance of this 0. It's crucial for this system that we have a 0. Let's illustrate that with this second example here. So we have another number recorded on the abacus. This time we've got, how many are over here? By the way, I can figure out how many there are over here by noticing that there are 3 over here. Okay, I know that if there's 3 on that side, there's going to be 7 on that side. It's one of the things that you learn by playing with an abacus. Actually a very important thing to learn. That 3 on this side means 7 on this side. If there's 1 on this side, how many are there on this side? 9. If there's 5 on this side, how many on this side? 5. So you learn to match 5 with 5, 4 with 6, 3 with 7, 2 with 8, 1 with 9. Those are very important matchings. They match up, they add up to 10. So we see that there are 7 ones moved over. There's 1 10 moved over. There's no hundreds moved over. All 10 hundreds are still over here on the left-hand side. Okay. Then there are 5 thousands moved over. And it looks like we've moved down a level. We've got even a bigger number. We've got some new kind of unit, of which there's 2 of them. And these units should be 10 times as big as the previous one. So they should be 10 times 1,000. Well, we don't have a new name for those units. We could, but the standard thing is just to call them 10,000s. So we have 2 10,000s. Now the Romans didn't have a symbol for 10,000s, but we would like to have a symbol for 10,000s, and so we're going to augment our Roman system a little bit, and allow me to introduce T for 10,000. Okay, this is a long overdue improvement on the Roman system. We're now going to add T, so that means we can talk about bigger numbers than the Romans used to. So this number that we've recorded here in Roman form would be, well, we start with the biggest ones. T, T, and then M, 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 and then, well, there's no C, so we wouldn't write down anything. We would go to the tens, there's 1 10, and then there are 7 ones. So we make no mention of the fact that there aren't any C's. You can see that there are no C's because you can't see any of them. There's no need to draw special attention to them. However, when we go to the Hindu-Arabic system, things are different. Because in the Hindu-Arabic system, every line counts. We have to record what's on every line. Just because there isn't anything on a line doesn't allow you to ignore that line. You still have to put something down. And that's where the 0 comes in. There are 0 hundreds because we have a symbol for 0. A new symbol that essentially none of the ancient cultures had. So we have 7 ones, 1 10, 0 hundreds, 5,000s, and 2 of these new 10,000s, and we're going to string them all together. Starting with the ones on the right-hand side, 7 ones, 1 10, 0 hundreds, 5,000s, 2 10,000s. Or if we had started from the Roman number, we could start either from the right or the left. Let's start from the left, sort of more in keeping with the spirit of things. So the 2 T's would be 2 10,000s, and then 5,000s, 0 hundreds. There aren't any hundreds, but we have to record that because this is the hundreds position. 1 10 and 7 ones. To see what position it is, it's often a little bit easier to start from the right because then you're guaranteed that you're going in the right direction. We can say that's the ones, that's the tens, that's the hundreds, that's the thousands, that's the 10,000s. You know you're in the right spot because every time you're going up by 10. And note that we're introducing a small convention. We're putting a comma right here. That's just a little bit of a helpful device to make it a little bit easier to see where things are. So we put the comma after the first 3 digits representing the ones, tens, and hundreds. So after the hundreds, there's a comma before we get to the thousands. Right? And we would write this, we would say this as 25,017. We'll talk about the names for numbers later on. Right now, we're just going to write down this number. That's our Hindu-Arabic form for this Roman number or this abacus number. Now, I think we can be reasonably sure that the Hindus who first developed this system were probably thinking more in terms of an abacus than they were some other system. They had some abacus, they had some counting frame. They wanted to represent what was going on there, that number, compactly. And makes a lot of sense just to record how many there are in each row. So from a counting frame or abacus point of view, the Hindu system is very natural. Okay, so that's good. We've introduced our basic number system that we're going to be working a lot with in this course. So now it's time for a few exercises for you. So exercise 4.3, solve these arithmetical problems in the framework of the simplified Roman numerals. So here's an addition question with actually 3 things being added. Here's an addition question with some bigger numbers. Here's a somewhat smallish multiplication, not too small though. And here's a kind of a bigger multiplication because that's 100 there. So in each case, I want you to think about what does it mean, what do these questions mean geometrically in terms of rectangles? Can we figure out what the answers are just using geometrical intuition, maybe drawing some diagrams? This one here, you may have to do some lateral thinking, because this rectangle here would have 101 rows and 11 columns, so it'd be pretty big to draw. So you might think, well, is there some snappy way of doing that? I want to get across to you that multiplication is quite a lot more difficult than addition. We're going to see that major theme in K-6 mathematics. In this question here, we're solving for a mystery number represented by a question mark. So this number plus some mystery number is this number, and you're supposed to try to figure out what the mystery number is. Here's another one. Here's mystery number plus 3 equals 1010, and mystery number plus this equals 100. And our last exercise, just to convert these into Hindu-Arabic numerals. Now that we have at least some terminology, we can now use our Hindu-Arabic numerals. I don't have to keep saying 1, 1, 1. I can talk about 12 and 13 a little bit. We're going to go back to the basic laws of arithmetic now. And we want to understand the laws of arithmetic from a geometrical point of view. So we're going to go back almost to this kindergarten approach and now ask ourselves, well, how does one actually, how does one actually multiply? How does one actually add? How do we figure out efficient ways of doing that? That kind of question is best addressed by going back to the more primitive kindergarten form of numbers as row rectangles. So I hope you'll join me for that. I'm Norman Wallberger. Thanks for listening.